So today we are going to start, like I said, Unit 2. Unit 2 switches gears a little bit. Most of Unit 1 hopefully felt like a lot of review, or at least reapplying some of the same things that you learned. And sorry for that. So recording is going to jump there a little bit because of that phone call, but we'll power through. So Unit 1 was mostly review, reusing a lot of the same skills, solving equations, simplifying expressions. We did introduce inequalities as well on top of that. But for the most part, the goal was usually the same. Expressions, we simplified best we could. Equations, the ultimate goal was to get that variable by itself. Unit 2, however, is going to switch gears some. And we're going to look not only at the algebra that's working, but we're also going to look at a graphical aspect and introduce this concept of what's called a coordinate plane. So our end goal over the next handful of lessons is going to be able to take very unique relationships that, when graphed out, actually form a line. So we're not just solving for answers anymore. Now we're trying to solve and find lines that we can then see on a graph. Now, because we are switching gears, that does mean that we are adding some new vocabulary words, which I don't worry too much about specifically. I think there is a vocabulary section on the test, but it's like a word bank, fill in the missing word from the sentence. But anytime that we introduce some new words, I try to put it in the context as well as show you what each of them look like. So the first thing we have here is a coordinate plane. Most people typically just refer to it as a graph, but a graph can take on many forms. This very specifically is a coordinate plane, which allows us to graph two-dimensional objects, up to two-dimensional objects. And it's usually split into what's known as 4 quadrants, 4 unique sections of the graph. And that split is in part thanks to the x-axis, which, if you notice on this coordinate plane, is the horizontal, slightly darker, also labeled axis, which is describing either a left or a right direction. And it's also split by the y-axis, which is the vertical axis that's a little bit darker, also with labels. And at the very middle, where these 2 points intersect, actually has a special name called the origin. So origin, especially if you're into superhero movies, you have an origin story. It's kind of like the starting point. And that's actually where we're going to start a lot of the times when we're dealing with our graphs today. Now, the whole idea of you have to crawl before you walk and then walk before you run, we're in the crawling stages right now, because in order to navigate around this graph, we need to know how to describe specific locations. And to do that, we're going to introduce this idea of an ordered pair. Now, that ordered pair is going to be made up of 2 numbers. They could be positive, they could be negative, they could be really any value you think of, where the first one is going to be what's known as the x coordinate, and the second value will be what's known as the y coordinate. They'll be separated by a comma. They will be wrapped in parentheses. Now, quick side step. Anyone in here ever play chess or battleships? Or there's another one, I always forget it. I think of it off the top of my head. But is anyone, maybe you haven't played it in a long time, but are you familiar with the concept of battleships? That one's a little bit easier to describe, where you and another player have ships on a map, but you can't see the other players. You're trying to sink all of their ships, but you don't know where they're at except by firing shots, and either that you hit them or you miss them. And in order to keep track of where you fired, you have a grid. And the way you call out your shots is by calling a row and a column. The rows, I think, are the ones that are labeled with a letter. So you say like B4. So you look on your graph, your layout, and you look for the square that's in the B row in the 4th column. and then you tell them either it was a hit, in which case your ship does exist in that square, or it's a miss because there's nothing there. And that actually allows you to describe the same exact location with the other player without actually seeing each other's maps. Coordinate planes work the same way. What about, has anyone ever used a GPS system? Not just like the one in your car or the one in your phone that says turn left, turn right, but has anyone ever seen a GPS system that gives you latitude and longitude?
Maybe seen them in movies, but
Okay, so maybe seen them in movies, but never actually used them. They do exist. You can purchase them, but it also means you have to know how to interpret the latitude and longitude. But what's interesting is any position on Earth, no matter where you're standing, can be described by a precise set of coordinates. Your latitude and your longitude, how far above or below the equator you are, how far to the left or the right of the prime meridian you are. And that describes a specific location on the planet. All that aside, basically by using coordinates, you can describe specific locations without actually seeing them or actually being there. And that's going to be kind of our goal here to begin with, is we want to find some very specific locations, and to identify them, once we find them, we're going to put a point there. And I'm also going to label them just so we remember which one is which. Now, before we actually practice on this set of ordered pairs, I want to give you some clues here. So this again is the template. It's going to be, again, wrapped in parentheses, x coordinate first, comma, and then followed by the second coordinate, which is the y coordinate. The x coordinate is going to tell you one of two things. Oops, wrong tool. There we go. So how far left or right you're going to travel, and this is with respect to the origin. The origin is always going to be our starting point. So the x coordinate is going to tell me either to go left or right. It's also going to tell me how far. Any ideas how to distinguish whether you're going left versus right? Give you a clue. We've kind of actually already dealt with this scenario a little bit. If you imagine for just a moment, if you were to ignore all the grid marks and everything else, the x-axis really is just a number line. Origin is our 0 in the middle. What can you tell me about all the values to the right of the origin? They're all positive. Increasingly so the further right you go. What about all the values to the left of the origin? They're all negative. So by simply looking at the sign, that's going to tell you which direction, whether it's left or right. And then the value itself tells you how far. So I'm going to sketch this in here real quick. So left is going to be our negative, right is going to be our positive. The y coordinate then, because it's not very interesting if we just traveled left or right, the y coordinate is going to tell me or answer the question, how far to travel either up or down. Wish I wasn't so picky about my notes. Now, you're welcome to look at your coordinate plane. Look at the y-axis. How would you describe the up direction? What's going to be unique about those values? They will be positive. So up will be a positive value, and down then must be negative. So, in simply just two values written in this structure tells me a lot of information. How far left or right to go, followed by how far up or down to go, depending on the sign, depending on the value, depending on the order in which you follow them. So we're going to try these out. Try to fit all of this on here. We have what's known as a set of ordered pairs. A set you can just think of as a list. And in that set, we have a total of 6 ordered pairs. So when we're done, we're going to have 6 unique locations identified across our coordinate plane. And every time that we graph, we always start our counting back at the origin, back at that 0 mark in the middle. So I'll do the first 3 with you, and then I'll give you a moment to try the last 3. -5, -4. So again, I'm going to start here at the origin. What's that -5 telling me to do? Go left how many units? So 1, 2, 3, 4, 5. And then the -4 is going to tell me to do what? Go down 4 units. 1, 2, 3, 4. And where that lands me is this location right here on my coordinate plane. So in case you can't see it, I'll zoom in here. This is describing a very precise location by using the coordinates -5, -4. Okay. Which in theory then, whether we're in the same room or not, whether we can see the same graph or not, if I were just to send you a text message or call you over the phone and we both had the same coordinate plane, I could tell you, okay, I have a point at -5, -4. You would be able to find that same location without actually seeing where it's at on my graph, which is going to allow us to relay information back and forth at a greater detail than what we could before. Next one here, 3, -1. So I'm back at the origin again. 3 is telling me to go where? To the right. How many units? 3 units. So 1, 2, 3, and then followed by a -1, which is going to tell me to go which direction? Down. How many? Down just 1. So I am 3 units to the right and 1 unit down from where the origin was, which gives me the ordered pair 3, -1. So far, so good. Next one, a little bit unique. 4, 0. So I'm back at the origin again. Where's the 4 telling me to go?
To the right.
To the right. How many?
4.
4 units. So 1, 2, 3, 4. And then where's the 0 telling me to go?
Stay right there.
Yep, stay right there. 0 tells us up or down, but in this case, we're going 0 units. So I'm trapped on the x-axis, and that happens from time to time. So what I'm going to do for just a moment, we did the first 3 together. I'm going to sit here for just 30 seconds or so. Go ahead and try to get the remaining 3 on the coordinate plane as well, just to kind of practice it. Okay. So I'll go a little bit faster on these. So assuming I'm back at the origin, where did you travel to get to the ordered pair -1, 6? Left 1, up 6. So 1 unit to the left, 6 units above where the origin started at, which takes us all the way to this top edge of the graph. We can still squeeze it on there, so we're good. What about 0, -2? That was another slightly tricky one.
You go to stay at the 0 and then you go down.
So stay at the 0. I like that you described it as staying at the 0. So the X coordinate usually tells me to go left or right, but a value of 0, I'm not going anywhere. But then the Y coordinate does tell us to go down 2 units, which has us on the Y axis down here at -2. And then last but not least, 4, 5, where are we going there? Right. Right 4, and then from there, up 5. So 4 units to the right, 5 units up from the origin. Gives us the ordered pair 4, 5. Now, I always have to ask, was anyone tempted to connect the dots? Now, if not, that's awesome. You're sitting pretty well. Sometimes I have students who are very tempted to think, when you see a bunch of dots, you kind of go into, oh, connect the dots mode. This is going to form something. That's not exactly what we have here. In fact, I know I said we're going to be graphing lines eventually, but these points, aside from being listed together in a set, don't have any kind of unique relation to each other. Think of them as just scattered points across a coordinate plane. They're not special in the sense that they form something greater. Just points, just locations. So I got to ask real quick, if I continue to give you more points, could you continue to graph them on the coordinate plane? It would get pretty crowded. What if, say, hypothetically, I gave you an even bigger grid with slightly larger values in the ordered pairs? Would the process remain the same?
Yes.
Yeah. Eventually, it's going to get kind of boring, and especially if you're counting, 50 units out or things like that. Which thankfully, there's technology out there that allows us to graph those things more quickly, and I'll actually show you some of them here. If not today, probably tomorrow. But think of these as the building blocks. If you can find specific locations on a graph, if we have a series or a set of specific locations that have a unique relation to each other, those locations are going to all come together to form something a little bit more impressive. So if you can graph points, we're going to be able to graph anything that we want today with a little bit of algebra thrown into the mix. So that's where we're transitioning into next. So we're going to be graphing what are known as linear equations. We've actually been solving very unique types of linear equations, but these are a little bit more generalized in the sense that what are some of the differences that you see? If you want to use this first one as an example, y equals -2x + 3. What's different about this one compared to all the other equations we've looked at so far? Okay, so one of the variables is already on one side. So one of them is technically already by themselves, but the biggest change would be that there are 2 different variables. So now it begs the question, which one do I get by itself? Well, we'll actually drive that conversation a little bit further tomorrow, but we still actually have a bag of tools or tricks that we will be able to accomplish pretty much anything once we know what we're trying to accomplish. This is basically what we're going to do here. But before I can show you all the little tricks and shortcuts for linear equations, we need to use a method that is kind of a fail-safe for any graphing scenario. Now, I have mixed feelings about it because I personally, knowing that there's a better way to graph linear equations, This one drives me crazy, and very quickly, you're going to be tired of it too, because the process we use today is very repetitive and dull. Not, some of it's challenging just because the occasional fraction thrown into the mix, but it's just really just boring. But I need to show it to you because in the event that you're ever asked to graph any type of equation, whether it's linear, like the ones I'm showing you today, or quadratic, which is going to be a type of equation you'll graph with Andrea in Algebra 2, or trigonometric, logarithmic, exponential, piecewise functions. There's a long list that where if you can do this process I'm about to show you, as boring as it may seem, you can actually graph almost anything with just enough patience. So let's see what I'm talking about here. So linear equations represent a very special set of infinitely many ordered pairs, which together form a line. So I'm actually going to highlight that whole sentence there. So linear equations is a special set of infinitely many ordered pairs together forming a line. So if you think about it, if I draw a line, any old line, and you don't have to write this, but how many points are on that line? If I were to zoom in really close, an infinite number, because if you think about it, however you want to measure it, you can measure to the nearest whole number, to the nearest half, quarter, eighth, 16th, third, 1/27th. The closer you zoom in, there's going to be closer and closer points. For the same reason, throw it over to science class for a moment. We're made up of really small little points, aren't we? Called atoms. Now, right now, it seems like we're solid, but in reality, if you zoom in close enough, I'm just made up of a bunch of atoms. Lines are the same way. There are infinitely many points along that line. And another cool thing about a line is because of the arrows at the end, that tells me that it goes on forever as well. All we need to do, fortunately, is just find a handful of those points so I can at least see where that line exists as well as where it's traveling. So what we're going to do here, we're going to be given some linear equations, and we're going to create a table of values in which we choose several x values, plug them into the equation, and find each y value that they are paired with, because that's really the end goal. We just spent some time graphing ordered pairs. We want to find the ordered pairs that are unique to each of these equations. So it may be a slight oversimplification, but I'm going to underline create a table of values. We're graphing using a table today. Now, depending on the last time you were in any kind of math class that uses this, there's a few different names. I usually use table of values. Some people say T tables or XY tables. They're all typically referring to the same thing. The way I like to set mine up, let's write mine off to the right here, is that there's usually two columns. One for all the X values that you're going to choose, and one for all the Y values that will pair with them. Now, our table is very empty at the moment. But if I refer back to the little prompt up above, we can choose several X values. Is there any conditions or any rules or constraints that says that we have to choose specific X values? Or can I choose literally any number I think of?
You can choose a number, but the bigger number you get, the more across the graph. So
I like where your brain's at. So spot on. Jay said, yes, we can choose any number, but if we're not careful, the larger values we choose, they're going to spread out very quickly across our graph. And is our coordinate plane that big? No, in fact, if you look at the X values that are currently listed, they only are listed as far as -6 to the left, +6 to the right. So if I chose an X value of like 73, I'd be so far off the edge of my graph, I'd be able to crunch the numbers, but I wouldn't be able to see it. Because imagine for a moment, this graph is a keyhole. We're looking through a teeny tiny space, and we're trying to find where that line exists. Now it goes on forever, but we're just looking at a little tiny snapshot of where it's at. So yes, we can choose any X value we want. Will we want to choose X values though that are too big for our graph?
I think usually unless you're specified some specific numbers, each 0, 3, 10.
Okay, so, and it really comes down to personal preference at that point. So my general recommendation in this scenario is, because I don't know where this line is going to exist, I'm going to try to stay as close to the center of my graph as possible. So 0 is always a great number to choose, because 0 plugged in anywhere, 0 times anything is always 0. And it's also really easy to add or subtract with zeros, because they don't change anything there. So 0 is always a great one to have in your list. From there, it's up to you if you want to use 1, 2, 3, or maybe -1, -2, -3, or maybe a combination like -1, 0, 1, 2. But I try to stick towards the middle of my graph when I'm choosing X coordinates or X values. One other question before we start picking some: could I theoretically choose fractions or decimals?
Yeah.
Sure. Who wants to calculate with fractions or decimals? I try to avoid it if I can. It's good to know how, but if you can avoid it, it's going to save you a little bit of time. But technically, again, when I say you can choose any X values, I literally mean any X value could be chosen. Some of them are just a little bit easier or more useful than others. So for this problem, I'm going to recommend we stay kind of close to the middle of the graph there. And for the sake of practice, I'm going to choose 4 points: -2, -1, 0, and 1. Relatively small values, threw in some negatives in there because in reality, if we need to practice anything, it's probably those negative signs that usually trip people up. What I have now are 4 X values. The problem though is I know how to graph ordered pairs. Are these currently ordered pairs? No. What are they each missing? Well, we have the X's, the Y's that go with each. Well, do I have anything else up here on the screen that has something to do with both X's and Y's?
Is it the 3?
Sorry, Angela, you were a bit quiet there. Can you say that again for me, please?
Is it the 3?
The 3, well, you're getting close. There is a 3 involved. I'm looking for something a little bit more general. I'm talking about this whole equation altogether. Because if you think about it, we know our X's, and it just so happens that there's an X in this equation. What are we missing? All the Y's. Well, there's also a Y in that equation, and very conveniently, that Y is actually already by itself, which is nice in terms of solving for things. So what we're going to do, this is the boring part, is one at a time, we're going to drop an X value right here where the X is at, crunch our numbers, and see what we get in return for the Y that goes along with it. So I have 4 X values. How many sets of work am I going to have? 4. And again, like I said, this is the boring bit because it's very repetitive. So I'm going to squeeze mine down here beneath the graph. And the first value I have is X equals -2. So in the equation we were given for this one, y equals -2x plus 3. When I get to that y, I'm going to swap it out. Excuse me. When I get to that x, I'm going to swap it out for this -2 that I have. So that's going to become y equals -2 times, instead of x, I'm going to pull out the x, drop in the -2. I like to wrap things in parentheses anytime I make a swap. That way I know, this wasn't here before. This is a change that I made. And then, so -2 times x plus 3. So just to summarize, this is still technically y equals -2x plus 3. We just happen to have a value for x. So I'm going to throw in my little guideline here, which is too large now, just to stay kind of on track, stay organized. Y is already by itself. I like that. On the right, however, I don't quite know what y is equal to. So I'm going to think order of operations. Would I do the multiplication first or the addition first? Multiplication. So first step, y equals, what's -2 times -2? +4. Bring down the plus 3. And what's 4 plus 3? 7. So when x equals -2 for this particular equation, what I get in return is a +7. And just so I can keep track of which is which, and I'll come back down here in just a moment. In my table, I'm going to write that the 7 is paired with the -2, just to serve as a reminder. Like I said, this is boring, but we start over. We deal with our next x value. So the next one on my list was x equals -1. So I drop it in, y equals -2 times x, which is this time a -1 plus 3. Same process yet again. Y is still already by itself. Very similar. We're going to do the multiplication first. This time, -2 times -1 is going to give me a +2. And 2 plus 3 is going to give me a 5. So again, still the same equation. When you change what you put into it, you change what you get out of it. So when I plug in a -1 for x, I get a 5 in return for the y. And again, just so I keep track of it, slide back to my table here real quick. Pair the 5 with the -1. And then prepare myself to go again. So next one on my list, this is the one that I like. X equals 0. Still the same equation. Y equals -2 times x. This time my x is that 0 plus 3. Doing the multiplication yet again. -2 times 0 is 0. And 0 plus 3 gives me 3. So still the same equation. When you plug in a 0, you get a 3 in return. So on my table, I'm going to pair the 3 with the 0, just so it, again, serves my memory. Last but not least, we also chose an x value of +1. So I'll get y equals -2 times x, which is this time a +1 plus 3. Again, that multiplication is going to come first. -2 times 1 is a -2. And -2 plus 3 is a +1. So again, up here in my table, I'm going to pair a 1 with the 1, bring this up. You know, some of you are still jotting this down. But again, very, very, very repetitive. The only thing that changed each time was the X value that I plugged in based upon the X values that we chose in our table. It's extremely boring, and I'll be the first one to admit it. But that work was not for nothing. When I come back up here and I say, okay, I now have a completed table of values for at least 4 different values of X. What I have essentially done now is I have created a list of ordered pairs, which if you're a very visual person, it may help to imagine these as a traditional ordered pair: -2, 7, -1, 5, 0, 3, 1, 1. Now, some of you may already be ahead of me, which is great. But I want to see where these are now on this coordinate plane that I've provided us. So -2, 7, where's that taking me? Left 2, up 7. Uh-oh, I accidentally ran off the edge of my graph. Was there any way of knowing that originally?
No.
No. We're just introducing this idea of linear equations. We were just picking X values that we thought would be easy enough. But I'm here to tell you, sometimes they're going to run off the edge just because we don't know where those lines are yet. Now, can I guess about where it's at? Left
Yes.
2, up 7. It's somewhere right around here. And if you want to kind of put a very light point there just to see if it fits with all the others, that's fine too. But I'm going to move to the next one that should hopefully fit on my graph, which is -1, 5. Where's that one?
To the left.
To the left 1
To the left 1 and up 5.
and up 5. So 1 unit to the left, 5 units up. What about 0, 3? Stay on 0, but then go up 3. And then the last one there, 1, 1. Right 1, up 1. Now, again, if you decided to earlier to try to imagine where that -2, 7 is, I would say it may be about right there. Again, I'm approximating because the grid marks don't go all the way up there. But what do you notice about these points?
Line up.
They seem to form a line. In fact, as long as you're graphing carefully and as accurately as you can, if you were to grab a straight edge, whether it's a ruler or the side of a folder or what have you, you should then be able, oops, didn't want that one, to draw a line through all of your points. And the reason for that is because that equation was a linear equation. All linear equations, when graphed, form a unique line. So every unique linear equation out there is going to give you its own unique line, depending on where it's at, where it's located, and which way it's traveling. Right now, we have no idea where it's going or where it's starting until we do a little bit of this legwork here. So is this extremely boring? Absolutely. Is there a better way? Yep, I'll show you that tomorrow. But we gotta walk before we can run. So naturally, I gotta pick up the difficulty a little bit because inevitably, with most linear equations, there will at least be one fraction involved a majority of the time. Now, tomorrow, that fraction is actually going to be tremendously helpful. Today is going to be a tremendous pain in our backside because we're going to have to calculate with that fraction. Now, if you're a little hesitant with fractions, talk with me. I can show you some neat tricks on the calculator. I can show you, the math behind it. Hopefully, if you came from math A and B, hopefully you spent some time there practicing your fractions. But it does add a slightly more interesting layer of challenge to this process that we work through. But the process remains the same. So what I'm going to do here for the second one, very similarly, is I'm going to set up a table of values. In fact, I'm just going to go ahead and use the same 4 values we had before. They seem to work fairly well the last time. Why not see what they do this time? So I'm going to use the -2, the -1, the 0, and the 1. The only thing that's changed now is the equation, which means even though we're plugging in the same list of numbers, what we get in return most likely will be different. So I'm going to come down below here, start to set myself up here. First one we're looking at is x equaling -2. So in my equation, what that's going to look like is we're going to have y equals 1/4 times x, but I'm going to pull that x and in its place put the -2, and then follow that up with the -1. Am I going to do that multiplication first or the subtraction first? Multiplication. Now, I'm going to be your calculator for right now. If you're still a bit hesitant with fractions, let me know. I've got all sorts of tricks. I'll help you find the one that works best for you. One of the tricks I like to use just kind of off the top of my head is if you're multiplying an integer with a fraction, all you technically do is multiply it with the numerator. So -2 times 1 is going to give me a -2/4.
You like to decide right out like steps for getting rid of the fraction.
For getting rid of the fraction?
What you just did. Yeah.
Sure. So let's see, let me do it off to the side here. So technically I'm taking 1/4 times -2/1. The great thing about multiplication with fractions is you don't need a common denominator. All you do is multiply straight across. So 1 times -2 is going to give me a -2 over 4 times 1, which is going to give me a 4. Now, does -2/4 simplify? Well, 2 and 4 both can be divided by 2. And if you were to do that, this fraction would simplify to a -1/2. Now, again, now we're dealing with subtraction with fractions, which is a little bit trickier, but with a little bit of money thinking. If I am half of a dollar in the hole, in other words, 50 cents, and I lose another dollar, I'm going to be further into the hole, which in this case has me at y equaling -1 and 1/2. Again, like I said, I've got some tricks that I can show you, especially with fractions involving addition, subtraction, multiplication, and division. Calculators are great tools so long as you know how to use them appropriately. But for our purposes, I'll be the one here to kind of speed up the process for you. when you plug in a -2 into this particular equation, you're going to get a -1.5 in return. So up here in my table, just so I don't forget about it, oops, next to the -2, I'm going to write -1 and 1/2. Some of you are thinking, but Josh, how am I going to count 1/2? We'll get to that in just a minute. Because next up, I'm going to plug in a -1. So I get y equals 1/4 times a -1 and then -1. 1/4 times, oops, forgot my little guideline here. 1/4 times -1 is going to give me a -1/4 -1. And when I subtract those, I'm going to get -1 and 1/4. Not what I wanted to do. So again, we're dealing with some relatively smaller numbers here. Again, I wouldn't necessarily have known this until I dove into this problem head first. So back up here in my table, -1 for x is paired with a -1 and 1/4 for y. And then I come back again to continue to repeat this process.
Do you just do like the regular subtracting for that one? -1/4 - 1.
Yeah, -1/4 -1. If you're already, try to think, there's lots of ways to think of it, and I never remember which.
Because whenever I see that, I think that I have to go out and do a whole thing where I come up with it.
Technically, you do. So I did this one in my head. So side note real quick. -1, so don't write this down. -1/4 -1, which is seen as 1/1. In order to add or subtract fractions, you have to have a common denominator, which we do not. But I could get a common denominator of 4 by multiplying the top and bottom of 1/1 by 4. So rewritten, this is -1/4 minus 4/4, which, let me pause for a moment. Isn't 4 divided by 4 still just 1 in disguise?
Yeah.
Sure. At that point, then, once you have common denominators, the denominator is going to stay the same. But then you're going to subtract the numerators. -1 take away 4 is -5. So you end up with an improper fraction, at which point I ask you, how many times does 4 go into 5? Once, which gets me to 4. Still have the denominator here. 4 is how many away from 5? 1. So did I do a lot of that in my head? No, actually, I just thought of it in terms of money because this one was a little bit easier, but mathematically, that is what's going on behind the scene. Now, the reason why I'm not saying you have to do it to that level every single time is because everyone in here has a different comfort level when it comes to fractions. Now, Jay, if you need to see that, please do that. If you're curious and like to see what a calculator can let you do, I will more than gladly show you. But it's hard to say that everyone has to do it the exact same way because not everybody has the same exact skill set, which is perfectly fine. So yeah, there is some math going on behind the scenes there. What was the next one? X equals 0. I like zeros. So I get y equals 1/4 times 0 minus 1. You know why I like zeros? Because anything multiplied with 0, fraction, decimal, or anything, is always 0. So 1/4 times 0 is 0. And then 0 minus 1 leaves me with a -1. So slide up to my table real quick. 0 is paired with a -1. And last but not least, x equals 1. So I get y equals 1/4 times 1 minus 1. =1/4 times 1 is going to give me a positive 1/4. Take away 1. So imagine for me for just a moment, there's $0.25. So think of this as 25 cents in your bank account right now. And you pay for something that is exactly $1. Are you going to overdraw your account? Yep. By how much? 75 cents. You're going to overdraw it by 75 cents, which is how much of a dollar? 3/4 or 3/4 if you think about it. So we're going to end up with -3/4 or 3/4. Again, if you need to see the math behind it, I'll gladly show you that kind of later on the side. But for our purposes, I'll be your calculator for right now. 1 is paired with a -3/4. Let me bring it back down here. I know some of you are still jotting this down. Pause there for a moment so you guys can do that.
You're gonna make the fraction ones a lot.
Only a handful today, but again, the good news is I'm going to show you a more efficient method tomorrow. A method that kind of uses that fraction as a strength instead of a frustrating situation where you're dealing with a fraction every single time. So only a handful today. But it is good practice for your fractions. So the next annoying part is that we do now have ordered pairs with fractions in them, but they can still technically be graphed. Because if you can count by whole numbers, technically, you should be able to count by fractions. Same reason is if you can use a tape measure, you should be able to count by fractions. Because what are the odds that anything's ever measured to the nearest whole number or the nearest inch? Very, very slim. So, yep, we're going to have to deal with these very carefully, and they're going to be kind of crowded because we didn't even know what was going to happen to this line until we started to do the work. So where's -2, -1.5 going to be? Start with what you know.
Go to the left, -1.
2 units to the left, and then from there,
Go up 1.5.
almost. It is negative, so technically we will go
Down
1.5. So we're going to be, I'm going to zoom in here because it kind of helps to see it. We're going left 1, 2 units, and then we're going down not just 1, but half a unit more. So we're not going to make it to -2 going down. We're going to be kind of in between the -1 and -2 marks. So again, this is the frustration with these fractions, because depending on your eyesight, the human eye is flawed. Even if you have perfect vision, you still are approximating. You're doing your best guess. So I'm going to keep it zoomed in here. What was the next ordered pair on our table? -1, what? -1 and -1 1/4. So we're going to be left 1 unit, down 1 1/4 of a unit. So even closer to the -1. So again, I do have the advantage because I can zoom into my screen, but this is actually a good example of why using a table sometimes isn't the most useful method. although it is still successful, it's just frustrating. What about the next ordered pair on our list? 0, -1, that one I can do. That one's on a nice grid mark. And then the last one, I believe, was 1 and -3/4, which if you think about it, you're going to go 1 unit to the right and you're going to go down 3/4. So not even a full unit, which is going to land you right there. So despite having those fractional increments, is it still seeming to form a line?
Yeah.
Absolutely. It may be frustrating because they are very, very close to each other, but part of that reason is because this is just not a very steep line. And we wouldn't have known this yet until we started to crunch those numbers. Now, trick question. How many points are on that line? Oh, good. Do you know what a lot of people say at this point? 4, because we graphed 4 of them specifically, but there are still infinitely many points, which means if I wanted to, my tables I've been setting up have had 4 ordered pairs in them. Could I theoretically do 40 ordered pairs? Could I do 400 ordered pairs? I'd have to have a lot of patience, and I'd have to have a lot of paper, and I'd have to have a really big coordinate plane. But theoretically, I could do it. I could have 4,000 ordered pairs. Now, they're all probably going to be, if you're only going by increments of 1 like we did anyone notice that it was only raising by 1/4 of a unit? That meant that if I continue this pattern, it would only increase by 1/4 of a unit every single time. There you have it. We can graph linear equations by slowly but surely working through the process of building a table. Now, what's cool is there's computer programs out there that you give it the equation, the value you want it to calculate, and it's going to. You have a question, Kristen? If so, we can come back. So again, really tedious, but still productive, still successful, just frustrating. Now, fortunately, there are a few shortcuts that I can show you today, because for the most part, we graphed 4 points. In fact, if you wanted to do the bare minimum with a table, the very fewest number of points that you have to find are 3. You want to know why 2 points is just not enough?
I feel like mentally I know like how it would visually look wrong, but I can't put it into words because it wouldn't look very, nothing that's ever going to look even, but it's, if you only have 2, you can't really differentiate what direction it's going to go in.
So that was actually a really deep way of thinking about it. Here's the explanation behind why it's not very specific in where your line's going. Think about this. Any 2 points you draw anywhere in space, what will they always form? A line. So the problem with that is if just one of your 2 points is out of place, you're going to successfully graph a line, but there's no guarantee that it's the right line. But throw in a 3rd point, it's a whole lot harder to draw just any old line with 3 points, because that 3rd point is going to have to be in the same succession. So 3 points is the absolute bare minimum, with one exception. If those 2 points that you're graphing are very special points. So 3 points is the minimum for a table. 2 points is the minimum if those 2 points are known as the x-intercept and the y-intercept. So for these definitions, I'm actually going to write 2 statements. The first line is going to be the what it is. The second line for each is going to be how to find it. So the x-intercept of a line is the point where a line intersects or crosses any guesses? X-axis. So the x-intercept is where a line crosses the x-axis, which therefore must mean that the y-intercept, I'm actually going to cheat here real quick. Check this out. It's not exactly the same though, because it's not where it crosses the x-axis, it's where it crosses the y-axis. So the x-intercept is where your line crosses the x-axis. The y-intercept is the point where a line intersects or crosses the y-axis. Now, if you think about being trapped on the x-axis or the y-axis, there's actually a neat little trick that allows you to find these points very, very quickly. And here's the reason why. I'll come back to this in just a second. But let's take a look real quick. Did we have any point on the x-axis at the very beginning of our notes today? Did we have any point on the x-axis of our very first coordinate plane today? Where was it at? At 4, 0. Now let me ask you this. If you were to pick any point on the x-axis, what would they all have in common? Well, they're all on the x-axis, but I'm just going to put a point here. This red point, what would its coordinates be? 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, -1, 0, -2, 0, -3, 0. What's the pattern? Sorry?
0 as their y.
As their y coordinate. And that's a fact. Any point on the x-axis always has a y coordinate of 0. So I'm going to come all the way back down to my notes here. The x-intercept, we can say, actually, how do I want to do this? So we'll say the y coordinate is always 0. So plug 0 into y to solve for what? If you replace the y with 0, you're solving for x. I'm going to highlight that. Oops. Now, guess what's true about y-intercepts? The exact opposite. So I'm cheating again. It's not the y coordinate that's always 0. It's the x coordinate that's always 0. So you'll plug 0 into x to solve for y. And if you're not sure, take a look at any of your coordinate planes, pick any point on the y-axis and think about what its coordinates would be. All of the points on the y-axis will always be 0 something. So I gave you the definition. I gave you a fact that is always true. I gave you in highlighted it's highlighted a summary as to how you can use that fact in order to find both the x-intercept and the y-intercept. So we're going to try those out here real quick. These go significantly faster than just setting up a traditional table of values. Because the table of values, we had at least 3 or 4 sets of work. Here we're looking for 2 very specific points, and we're plugging in one of my favorite values, which is a 0. Zeros are significantly easier to work with because they multiply very easily and they add and subtract very easily. So let's see it in action. So you'll notice this equation is written a little bit differently. There's no variable by itself. That's okay. I'll actually show you tomorrow how to get variables by themselves when there's still 2 of them. But what we're still interested in is that there's still an x in there and there's still a y in there. So we'll be able to perform the tasks that we need to in order to find the x and y intercepts. And I'm going to kind of chunk them out into 2 sets of work. So I'm going to start with the x-intercept. And just as a reminder, I'm going to write that y, I'm going to write next to it. Y always equals 0 for the x-intercept. Again, we wrote that down up above. This is just as a visual cue. So I'm going to take that exact same equation. When I get to y, what am I going to swap it out for? A 0. So that equation will now become 3x minus 4, and instead of times y, it's going to be times 0 equals 12. Now, do you know what I love about that 0? But what's negative 4 times 0? 0. And if you add or subtract 0, does it change anything? No. So for my purposes, negative 4 times 0 becomes 0 and no longer changes anything for me. So all that I'm left with is that 3x equals 12. How would you solve that equation? Divide by 3. This goes back to unit 1. 3 divided by 3 is gone on the left, leaving me with x. On the right, 12 divided by 3 leaves me with 4. And just like that, we have our x-intercept. So where am I going to put that point on the x-axis?
4 over to the right.
4 to the right, because I'm looking for the positive 4. So I put my point.
You can also rewrite it as a ordered pair.
You can,
Like I know you can like.
Yep. Because our x coordinate is 4, the y coordinate, which we already knew about, was going to be 0. So it's just describing the ordered pair 4, 0. Good question. Y-intercept, very similar process. Except what's different? The x equals 0 instead of the y. So same equation, except this time when I get to the x, that's where the 0 is going to go. So I have 3 times 0 minus 4y equals 12. But yet again, what do I like about that 0? Well, first, 3 times 0 is 0, but then at that point, it's gone. So it's not really going to change anything. So I can drop it out altogether. And what I'm left trying to solve is negative 4y equals 12. And how would you solve that?
Divide both sides by
Divide both sides by
-4.
a negative 4. On the left, we're left with y. 12 divided by negative 4 leaves me with a negative 3. So if you wanted the ordered pair for that one, we said the x coordinate was 0. The y coordinate we just found is -3. So we're looking for 0, -3. So really all you're looking for is the -3 on the y-axis. And because those are two very specific points, very unique points, I can then just connect them to get my line. And this line is very unique to the equation we started with. I know we're going a little bit over today, but you'll still get your short break. This one just takes time because of that. Those darn tables are just so repetitive. Let's try one more, a little bit quicker. 2 points. We're looking for the x-intercept and y-intercept again. So I'm going to set up my little workspace here. I'm going to start with the x-intercept first again, which tells me that y has to be 0. So in this equation, I'm going to have 5x plus 2 times 0, as I swap out the y, equals 10. You're going to notice that that 0 knocks out a term yet again, leave me with just 5x equals 10. And then how would I solve this? Divide by 5. So for this one, I get x equals a +2. And again, in terms of coordinates, that would be 2, 0. Then last but not least, y-intercept. For that, x is going to be 0. I'm going to have 5 times 0 plus 2y equals 10. 5 times 0 is gone. I'm really just solving 2y equals 10. And then to solve that, all I need to do there is divide both sides by 2. So what does y equal? 5. So that ordered pair, the x we plugged in was 0. The y that we got with it is 5. So 0, 5 is going to be up 5 units, still on the y-axis. And just like that, we get yet another line. So again, in terms of the amount of work necessary, this is scaled down significantly, but there's always a catch. Is there always a guarantee that both the x and y intercept are going to fit on the coordinate plane? No, and we won't know that until we try to find them. And we won't know that depending upon the size of the coordinate plane we have. There's also another unfortunate catch. Sometimes the x and y intercepts, all right, wouldn't be math class if there weren't some special cases to squeak in there. Here's the good news. These two special cases are the easiest to graph. They're usually the easiest to spot, but the bad news is they're also the easiest ones to get mixed up, to confuse one for the other. Good news is, though, I'm going to give you a little trick, and the same information will be provided on any kind of test so that hopefully you don't get the two mixed up. Excuse me. So horizontal lines. Horizontal lines, when you're looking at their equation, they are very, very unique in the sense that they won't have both an x and a y. In fact, they will only have a y, and that y will be set equal to some number. Any number, in fact. So for example, if I was to have y equals 3, the way I would graph that is I would find 3 on the y-axis, place a point, and then draw in a horizontal line.
Is that our speaker?
That's next door. Thanks for looking out though. That's it. Horizontal line, I don't have to find, I only have to find 2 points. I just have to find where it crosses which axis, and I just draw it in as horizontal, because horizontal always goes perfectly left to right. Like the horizon. That's a good way of thinking about it. Any guesses what a vertical line format would look like? It's going straight up and down. Any guesses about the equation? X equals some number. So it's literally the exact opposite. So for instance, let's say on the other one, we had y equals 3. If this one said x equals 3, they look very, very similar in terms of the equation, but they are significantly different on the graph. So for this one, you would find 3 on the x-axis, and you would draw in a vertical line. So like I said, easiest ones to graph, they're the easiest equations to look at, but they're also the easiest ones to get switched. To remember what x means this, y means this, which is why I would tell you that horizontal lines is y equals some number, vertical lines is x equals some number. All that I ask is you practice.